To understand why the sound changes so much when connecting a high Z output to a low Z input, you need to know about Ohm's law. Now, before looking at Ohm's law, let me first admit that I've always found it difficult to intuitively explain how to actually apply Ohm's law. But in researching for this video, I learned a really cool way of explaining it from the Alder Audio YouTube channel. It helped me a lot, and I think it's going to help you too. Ohm's law states that voltage equals current times resistance, or voltage equals I times R. In audio, we're dealing with alternating current though, so let's change that to voltage equals I times Z, or voltage equals current times impedance. The most important thing to understand right away is that impedance is similar to resistance, but it's frequency dependent, which is really important in audio, where we're dealing with signals that contain many different frequencies at the same time. While the specs I've shown you in this video state only one number for the input impedance or output impedance of the devices, that is actually just the impedance at a particular frequency, say 1 kilohertz. In reality, the impedance of any circuit will vary throughout the frequency spectrum. That means the impedance at 100 hertz is likely not the same as the impedance at 1 kilohertz, which is likely not the same as the impedance at 10 kilohertz, and so on. And this is critical because it explains why we don't just hear an overall level difference, but also a tonal difference when connecting high Z to low Z, because frequencies throughout the spectrum are not being impacted in the same way. For this discussion about impedance, let's rearrange Ohm's law so that impedance equals V over I. This represents the same relationship, just written differently, and when it's written this way, it becomes more apparent that impedance is simply the ratio of voltage to current. Again, this example comes straight from the Alder Audio YouTube channel, and I recommend you go check out that video. Say we have a 1000 hertz sine wave on the high Z circuit. The amplitude of the voltage in red is 10 volts, and the amplitude of the current in blue is 5 amps. Now these numbers are completely arbitrary. They're just simple values that we can use to plug in. Referencing Ohm's law, we can look at the ratio of 5 amps to 10 volts, and we know that the impedance of this circuit at 1000 hertz is 2 ohms. Meanwhile, a sine wave at a much lower frequency of 100 hertz might have a voltage of 10 and a current of only 1. In other words, at 100 hertz, the impedance is 10 ohms because the ratio of volts to amps is 10 to 1. So although these two sine waves have the same voltage amplitude on this circuit, as you'll see in a moment, they'll be impacted very differently when we connect this circuit to the lower impedance input on our mic preamp. The input of the preamp will have an input impedance. Let's say it's 5 ohms. And there will be an amplification circuit that reads the voltage of the signal, not the current, the voltage. In this case, because the input impedance is 5 ohms, we know that the ratio between voltage and current must be 5. So something has to come down, either voltage or the current, so that there is a 5-to-1 ratio of voltage to current. Nothing will be increased here. Something needs to be reduced. And this is where we start to see the voltage affected differently at some frequencies compared to others. In the case of 1000 hertz, the current is reduced to 2 amps, bringing the ratio of voltage and current to 5. Notice that the voltage stays the same, which is what our mic preamp responds to. However, in the case of 100 hertz, the voltage will need to be reduced to 5 volts in order to bring the ratio to 5-to-1. Now the voltage has changed, giving the 100 hertz sine wave a lower amplitude voltage than the 1000 hertz sine wave. The mic preamp responds to this relative voltage difference, and that results in a relative level difference between these two frequencies, which were equal in the original circuit. This is where we get to the guideline to structure your signal chain so that the input impedance of the receiving device is at least 10 times greater than the output impedance of the sending device. If you follow this guideline, ideally the voltage of the signal will never need to be reduced, only the current. I expect the real electrical engineers out there will say that this isn't a perfect explanation. And you're probably right. But for me, in the context of audio production, these explanations have been very helpful, and I hope they help you as well.